Okay, good afternoon. Let's continue with our discussion of diode circuits. We were looking at analyzing or analysis of diode circuits using a couple of different models, right? The two models were the ideal diode model, and the second model is a constant voltage drop or CVD model. It's okay. So any questions that I can answer before I move forward? Okay. All right. So CVD model and ideal diode model are essentially very similar, except for the modeling of forward bias. Meaning in the forward bias, in the reverse bias, both models will portray the diode as an open. In the forward bias, it's a short circuit, except CVD requires a short circuit plus the diode voltage drop. This diode voltage drop could be 0.6 or could be 0.7. 0.7 is pretty much the standard. And if it's not given, you can always assume it. Okay. So with these kind of semiconductor devices, if something is not present, then we simply assume. So you can assume 0.7 and proceed with your solution. Okay. So let's explain how this works. Let's first use ideal diode model and analyze the circuit. Okay. So if we, excuse me, if you're trying to plot the voltage transfer characteristics, meaning we are trying to plot the output voltage as a function of the input voltage. Output voltage V out is on the y-axis, V in is on the x-axis. And it's known as transfer characteristics because it is showing you the characteristics of the circuit and it's showing you how the input is transferred to the output. Hence the name transfer characteristics. And because it's talking about voltage, it's known as voltage transfer characteristics, or VTC for short. Okay, VTC. Voltage transfer characteristics. How is the input voltage being transferred to the output? Anyway, so if we use the ideal diode model, let's assume that V in is less than 0. Okay. If V in is less than 0, then the anode of the diode is held to a lower potential than the cathode, which means the circuit looks like this. And diode is open circuit. And my V out, what do you think is my V out? I'm measuring V out over here. What is V out? It's simply equal to V in. Nothing right now because it's an open circuit. And we are simply measuring the voltage between the terminals. If you're simply measuring the voltage, the multimeter has infinite resistance or very high resistance. So there's no current flowing in the circuit, meaning the voltage that we obtain in the output is exactly the same as the input voltage. So V out would be equal to V in. And that is what we see here in the third quadrant. So when I say here, this is what I'm pointing out. Third quadrant. Okay. In the third quadrant, V in is less than 0. So it's going negative, right? It's less than 0. So in all of this, V in is less than 0. And if V in is less than 0, then diode is off. V out is exactly the same as V in. Okay, V out is exactly the same as V in. For those of you who are online, if you have a question, feel free to speak up. Okay, just interrupt and speak up because I would not be able to monitor the chat window. All right. So does everybody understand that? V in is equal to, V out is equal to V in. And again, this is still the ideal diode model, not the CVD model. And then let's take the case where V in is equal to or greater than 0. And if that's the case, then my diode is on. If my diode is on, it conducts, and I replace it with a short circuit wire. And now if I measure V out, what is my output? 0. Absolutely. So again, fundamental concept. If you have two nodes in a circuit and both of those nodes are connected with a wire, then essentially they are the exact same node. If you try to measure voltage across the same node, there is no difference in potential, meaning output is 0. So then it would be a line that is lying flat on the x-axis. So your output would be like this. This is the origin, 0, 0. Here, V out is equal to V in. And here, V out is equal to 0. That is the quick and easy analysis using an ideal diode model. Okay, let's take a pause, think over that. Let me know if you have any questions. Make sense to everyone? Or are we still thinking about it?
Wait, what does the 0, 0 mean?
Oh, just origin. X equal to 0, Y equal to 0.
Okay.
Let me just, let's do this better. X-axis and Y-axis. So X-axis, we have V in. Y-axis, we have V out.
So if there's a resistor, why is V out still equal to V in?
Because, so question being asked is if there's a resistor, why is V out equal to V in? Is because the end where we are measuring V out is an open circuit. And because it's open circuit, there is no current flowing in the circuit. If there is no current flowing in the circuit, there is no voltage drop across the resistor, which means both ends of the resistor are at the exact same voltage. And so V out would be equal to V in. Does that answer your question?
Yes, it does. Thank you.
Okay. All right. So now we have the ideal diode model. Let's talk about the CVD model. What do we think would be the difference in the CVD model? Right. Remember what I said, that both models are exactly the same, except we have to account, or we must account for the diode voltage drop, just 0.7 volts. Right. So instead of 0 volts, the diode requires 0.7 volt. Excuse me. It requires 0.7 volts to turn on, meaning V in must exceed 0.7 volts. That's the only difference. No other difference. Okay. There is no other difference. It must exceed 0.7 volts. Below 0.7 volts, V in is equal to V out. Okay. So there is no other difference. So below V in less than 0.7 volts, the circuit looks exactly the same as the ideal diode model. Diode is open circuit. And V out is equal to V in. So if you apply 0 volts, you will obtain 0 volts at the output. Hence, you have this waveform. And then when you get to greater than or equal to 0.7 volts, now V out is equal to the diode voltage drop. Because from this point on, the diode is a short and you have 0.7 volts voltage source in series with that short circuit. So the model is this. Okay. Again, remember in CVD model, we are replacing the diode, or we are modeling the diode as a constant voltage source of 0.7 volts. And so it's a voltage source of 0.7 volts. So V out is equal to 0.7. So again, it's a flat line at 0.7. Everything is simply shifted up and across by 0.7 volts. That's all that happens on the graph. Okay. So I especially like to point this out because this is the first circuit we analyze with the ideal diode and CVD model. But going forward from here, we'll just look at CVD models. All right, let's take a pause while you think over this and let me know if you have any questions. All good? Does that make sense? Okay. All right, let's look at a few more circuits then. This is simply the LT Spice simulation. We are applying a voltage V in. We are simulating from -5 volts to +5 volts. You can enter your own values if you wish to do this. -10 to +10, -1 to +1. And we are using a standard diode, 1N4001. Okay, this is one of the most common silicon diodes that students will encounter. This is the diode that I studied and performed experiments in when I was a student. And then my professor studied the exact same thing, same diode. It's been around for a long time. Okay. So we create the circuit, measure V out across the diode. Then you can see V in can go from -5 to +5 volts, but V out takes a bend and remains constant at the diode voltage drop. Okay. There will be a slight curve in this because this is not an exact model. A diode curve, if you remember, it curves up, but there is a slight slope to it. The slope is exaggerated here, but is present in real diode. So when you run an LT Spice simulation, you might see a little upward looking curve on that V out characteristic. Okay. So this is something you can easily simulate. I would highly recommend you do. Circuit is given to you. And the answer is also provided. Okay. One question I should have asked here. What happens if you flip the diode? If you flip the diode, meaning you interchange the diode cathode and anode terminals. Would the entire x-axis be mirrored? Be mirrored where? Yes, it wouldn't be in that quadrant, no. So this creates a positive side or positive voltage limiting, right? Because in the first quadrant, the only output we get is 0.66 volts. We won't get anything else. And so if you flip the diode, the result will be exactly the opposite. Because it's now conducting in the negative range, and positive range is completely off. Okay. All right. So sine wave or sinusoidal waveforms have this form. Right? This is a sine wave. Mathematically represented with a sine and cosine function, hence it is known as a sine wave. If you apply a sine wave input, and there's a sine function here, and you're simulating from 0 to 5 volts, that 0 to 5 volts signifies that it goes 0 to 5 in the positive direction, and it also goes 0 to 5 in the negative direction. Hence, you see -5 to +5. Okay, so in LT Spice, you simply specify the value of one peak, and because it automatically recognizes sine wave as going positive and negative, it's going to generate that sine wave. Yes. Oh, question from the previous slide. What happens if we flip the diode? So the circuit would look like this, right? Here's our V out. Now for all values greater than 0, the diode is going to be off, right? So if, let's say, for example, if V in varies from +5 volts, oh, sorry, -5 volts to +5 volts, if it's +5 volts, diode is reverse bias, it's going to be off. And so for positive values, meaning V in greater than 0 volts, diode is off, and V out is equal to V in. And then when V in is less than 0 volts, diode is on, and so V out is equal to 0 volts. That would be the answer for this. Does that answer your question? Okay. So of course, this is with the ideal diode. Ideal diode model or CVD model. Exactly the same thing, except it requires now minus 0.7 volts or in the negative direction. Just on a side note, if you simulate this in LT Spice, there are 4 combinations you can try. You can try first this combination, right? Positive of the source is at the top, anode is at the top. Then you can flip the diode so that anode is at the bottom. Then you can also flip the voltage source so that the negative is at the top and positive at the bottom. So you have 4 combinations. You have the voltage source, you have the diode, both pointing in the same direction, both pointing in the opposite direction, and then flip both of them. So you have 4 possible combinations. And two of those are exactly the same. So 2 and 2, right? If you flip both at the same time, it's no different than this circuit right here. Now, computer simulation is easy. You just do it, click, and you already have an answer. But as engineers in training, you should spend time in understanding how it works and explain it to yourself. And then if you have any questions, you reach out to me. Okay. All right. So let's go here. Positive side voltage limiting applied to a sine wave. So it's the same circuit, but now the input has changed. Input is a varying. It's not a constant DC voltage. It's a sine wave, but the principle remains the same. Right? We don't care what the voltage value is at any given point in time. We only care whether it's positive or negative. That's all we care about. Okay. So if you wish to analyze this, again, starting with ideal diode, it makes it easier. But as I said, in the interest of time, I'm going to go straight to the CVD model. So in the CVD model, what happens? CVD model. And let's say V in is less than 0.7 volts, exactly what we had in the previous circuit. What happens if V in is less than 7 volts or 0.7 volts? It's off, right? So diode is off. My V out is exactly the same as V in. Right? So the point here is that the input voltage can take any shape it wants. All we care about for the purposes of this analysis is whether it's greater or less than 0.7 volts. That's all we care about. Okay, so this is exactly the same as the previous one. If V in is like a triangular shape or a rectangular shape or an arbitrary noise signal, doesn't really matter. Okay, as long as it's less than 0.7 volts, diode is off. V out is exactly the same as V in, and that is what is shown here. What is not shown is, well, the input's not plotted, but the input would be, sorry, not here. Yeah, input would be here in all of these points. And so what we say here is that the positive half cycle is clipped or it's cut. Okay. So another name for this circuit is that it is a clipper. Diode clipper. Because it's clipping one of the cycles or it's clipping the input at a certain level. And the other name for it comes from the fact that it limits the output voltage. So it's also a diode limiter. Okay, diode clipper. Or limiter. And then V in greater than 0.7, diode conducts, it's on. So the positive cycles, diode is like a short in series with a voltage source of 0.7. So V out is equal to 0.7 volts. And we see that here in these places right there. Okay, all of these indicate the diode turn on voltage. All right. Let's take a pause. Think over that. Let me know if you have any questions. Any questions? Okay. All right. Flip the diode. And you get the positive half cycle. Negative is cut. As practice, you should explain it to yourself on how this circuit works based on the previous slide. Okay, based on the previous two slides, if you will. Okay. All good? Okay. Now, here it says work with your neighbor, but I'm going to go work through the solution as we go along. Okay. So we have three circuits in the next three slides. You're asked to sketch the voltage transfer curve or the voltage transfer characteristics for each one of those circuits. Assuming CVD model with 0.6 to 0.7, let's simply take 0.7. All right, let's not have a choice there. So 0.7 volts CVD model, and we are applying V in on the left, splitting V out on the right. Okay. These are the ways the circuit diagrams are drawn. The actual circuit, if I wish to draw it complete, then it would look something like this. Five volts. Plus minus V out and plus minus V in. So this time V in is coming from the left, and we have a constant voltage source of 5 volts here. All right, so what do you think? Let's take a few seconds to think on it. Look at what is connected at the anodes and the cathodes of the diode. And then think about what is required or what value of voltage is required to turn the diode on or keep it off. Any ideas? Any thoughts? So the first thing we want to look at is, well, let's go along. We want to look at is whether the anode or the cathode is connected to a source. In this case, the cathode is connected to a source, which means the cathode is held at the value of that voltage source. Now, depending on how the source is connected, in this case, plus 5 volts is connected to the cathode, meaning the cathode is already at plus 5 volts. Now remember the condition, the anode must be equal or higher than the cathode in order for the diode to turn on. So if the anode is less than 5 volts, the diode is off. That makes sense? So it's essentially, it's no different than the other circuit. The only difference is that the cathode is held at plus 5 volts. If it's ideal diode, V in needs to just be at 5 volts for the diode to turn on. If it's CVD model, it needs 5 plus 0.7, meaning V in must be 5.7 volts or greater in order for the diode to turn on. Below 5.7 volts, diode is off. If diode is off, then V out is equal to V in. I should start awarding bonus points for students to speak up, then I'll have more participation. Anyway, so let's do again CVD model. All right, CVD model. If V in is less than 5.7 volts, it's less than 5.7 volts, then diode is off. And if diode is off, then V out is equal to V in, right? So we'd have something like this. Should be a symmetrical, and so up to here. Oh, yeah, I moved it a bit too much. And then oh, sorry, it's 5.7 volts. So it's got to go right there. Right, V out is equal to V in. And once it turns on, if V in is greater than or equal to 5.7 volts, diode turns on. If diode is on, then it behaves like a voltage source of 0.7 in series with the 5 volt source. So V out would remain constant at 5.7. That is the answer. Okay, 5.7. And again, with this circuit, there are multiple combinations you can try. You can flip the diode. You can flip the voltage source. And as practice, I will assign that for students to think about what will happen if you flip the voltage source and or if you flip the diode. Okay. If you flip the source, so let me just, in a brief few sentences, let me describe. If you flip the source, now the negative, so the cathode is now connected to the negative end of the 5-volt source. So then cathode is already below 0. 5 volts below 0. Okay. So the diode is always going to be on unless the anode falls below 5 volts. So then you have to think about what it takes to turn the diode off, not on. Because if the cathode is always held at minus 5 volts, diode is always going to be on. Require 0.3, it would require 0.7 volts to turn on, so 5 minus 0.7. But other than that, diode is always on. Okay, so think about that. That would be part of your homework learning. All right. Same circuit, but now you have an additional diode in parallel. So what do you get? As far as the positive side is concerned, so again, CVD model. Now we have 2 diodes, so there are 4 possible combinations, right? If we call this D1, we call this D2, we have 4 possible combinations in the circuit. Off and off, or off and on and off, or both on. Okay. So let's say V in is less than 5 volts. If V in is less than 5 volts, what is D1? Is it on or off? We just saw that in the previous circuit. Is D1 on or off? No one.
Off.
It's off. Actually, it's 5.7 volts. Because diode requires 0.7. But anyway, D1 is off. Right? What about D2? What about D2? If V in is less than 5.7 volts, what about D2? Check the connections. Is there a voltage source or a fixed voltage connected at any end of D2? Right there. The anode of D2 is connected to ground, which means the anode is held at constant, but what value? 0. Absolutely, you're right. So D2 anode is at 0, meaning in order for D2 to turn on, what must be true about the cathode? It needs to go negative by how much? 0.7 volts. So if V in is less than 5.7 volts, right now, as far as we know, D1 is off and D2 is also off. And if both are off, then V out is equal to V in. there's a subsection of this point, right? There's a subset of this point because we are only talking about V in less than 5.7 volts. But we already established the fact that if V in falls below minus 0.7, then D2 will turn on. That creates another subset of 0.1. Okay. So D1 is going to remain off no matter what, right? If the voltage is less than 5.7 volts, D1 is going to remain off. Do we all agree? Right? It would never turn on. This is the simple, not simple, sorry, the similar case from the previous example. But now, what does it require for D2 to turn on? Well, if V in falls below minus 0.7 volts, D1 remains off, D2 turns on. If D2 turns on, what is my V out? What is my V out? It's modeled as a voltage source.
Negative 0.7.
Absolutely, negative 0.7. And so it becomes like this. And you're taking V out right here. So let's write down that this is D2. V out becomes minus 0.7 volts. Okay, so my V out is going to look like this. Actually, I should have, let me draw this out first. 1, 2, and 3. Right. So minus 0.7 volts. And this would be plus 5.7 volts. Right. And that's the last case, which again is similar to the first one. So V in goes greater than 5.7 volts. D1 turns on. D2, of course, is going to be off. And so V out is equal to 5.7 volts. Okay. Let's take a pause, think over all of that. Let me know if you have any questions. Okay. We got 6 minutes left to cover a couple more slides. Does this make sense? Okay. As long as you're consistent with your procedure, taking it step by step, you will arrive at the right answer. A problem similar to this is guaranteed to be on the final exam. Okay, so if you want to note it down, I mean, I'll have it on the final exam page as we get closer to the last week of class, but you might want to note it down right now. Yes. So will you ever factor in? What do you mean by reverse voltage? Oh, question being asked is about diode breakdown. Diode breakdown. Zener diodes, yes. That'll come up later. Yeah. Yeah. Not from these. Okay. All right. Shall we move on to the next one?
Oh, wait, what happens if both are on? Is that possible or?
Both would not be on, not with this case scenario, no. We've covered all scenarios right here. Right? Because the two primary scenarios are whether it's greater than 5.7 or less than 5.7. And then a subset of being less than 5.7 is that how low can you go? Well, if you go lower than minus 0.7, that point D2 turns on. So there would not be any possibility when both are on at the same time. At least I don't see any possibility where both would be on at the same time.
Okay, thank you.
Yeah. All right. So this next one is, well, I would say exactly the same. The only difference is that there is an additional resistor in parallel. And if there's an additional resistor in parallel, then what we need to do is find the Thevenin equivalent circuit. So we need to take this is R, this is R, this is going into the circuit, this is V in, and this is going into our diode circuit. Okay. So what is the actual V in going into our diode circuit? Well, we need to find the Thevenin equivalent circuit. Which, because the two resistors are in parallel, we need to convert it like this. And goes joins into the circuit. This would be RTH, this would be VTH, and then the analysis remains the same from that point on. So I'm going to assign this as student practice. The exact same analysis. The only thing is we need to find VTH and RTH. So the values would change. Okay. So V in values would change. All right. It's only 1:59, so I'll leave the next slide or the last page for next class. But do this and then bring your answers to next class. And then we'll discuss the answers. Okay. All right, we'll end class here today and we'll pick up here on Friday. Monday's quiz will be based on ideal diode analysis, CVD model. Sorry, not ideal diode. Diode analysis using ideal or CVD model. And of course, I will announce that on Friday.